Thank you very much for the introduction. Can you hear me? Perfect. So at the microscopic scale, neural tissue is composed of individual neurons that can be connected to each other and that communicate through spikes. And so if we want to model a large network of neurons accurately, the resulting model is going to be very granular, which makes the mathematical analysis of this model challenging. One way to deal with this difficulty is to try to translate the original granular model into a fully continuous one, in hope that the continuous model will be easier to analyze and understand. To do this translation, most often one needs to take a limit, and in this talk we'll be only concerned by taking the limit n, the number of neurons, tends to infinity. In this spirit, an old question in theoretical neuroscience is whether we can approximate large networks of spiking neurons, so something very granular, by a population density equation, something completely continuous. And these population density equations are quite useful in computational neuroscience because with them you can study collective phenomena like synchronization, you can study information transmission. You can also use them to coarse-grain complex networks, like a cortical column. And you can also derive what's called the next generation firing rate models directly from spiking neuron models. And this is elaborated in these two references. So this was all very high level. Now I'm going to walk you through like a very concrete example. So take a leaky integrated fire neuron. So here a neuron has a voltage variable that grows with time until it hits a threshold. When it hits a threshold, it emits a spike and the voltage is reset to a certain value, a fixed value that we choose here to be 0 for simplicity. So I think most of you are familiar with this model. So now we take the same model but we take the same model, but with escape noise. And this means that we don't have a hard threshold anymore, like before, but instead, for each value, for each value V, each voltage value V, we have an instantaneous probability to emit a spike, that's called the intensity. And the intensity will be given as a function f of v. And we'll call the function f intensity function. So now the spike times are stochastic. And so a neuron can be seen as a stochastic process. We can now do an easy changer variable. So we go from voltage to age. And so now between spikes, we have this straight line because the age grows linearly with time. Sorry, I didn't explain what age was. So age is the time elapsed since last spike. And so we can go from voltage to age. And now in between spikes, we have these straight lines, but essentially it's exactly the same model as before. Sometimes it's useful to see neurons as particles because a neuron, like I said before, has a variable a, the age. So you can imagine a neuron as a point moving along this age axis. And so when there is no spike, the neuron moves to the right, and each time it emits a spike, it jumps to 0 instantaneously. And if you have many neurons, you can all draw them on this axis. And so if we have a network of n neurons, of course, we would like them to interact with each other. And so here we'll consider only the simplest form of interaction, which is mean field interaction, which means that all the neurons are connected to each other in a homogeneous way. So now the intensity function depends on a and x, and I will call x the mean field input. And the mean field input x will simply be the average over all the spike trains in the network convolved with the function h. And I call this function h the interaction function. So here I have described what could be called a mean field network of spike response model 0 neurons with escape noise. And in the mathematical literature, that would be called a mean field network of age-dependent Hawkes processes. So what happens when the number of neurons tends to infinity? So imagine that on its axis, you have more and more neurons. And I think we can kind of guess what's going to happen. And indeed, when n tends to infinity, you don't see the individual neurons anymore that are jumping around, but you just see a density rho. And this density rho evolves with time, and this evolution is given by a partial differential equation. So this is an example of population density equation. Just a bit of history on all this. So this n to infinity limit was conjectured some time ago by Wilson and Cohen and Gerstner. The equation you are seeing above is called the time-elapsed neuron network model of Pagdaman, Pertam, and Salor. And so these authors proved that this equation is well posed, and they did many analyses on this equation. And importantly, recently, Chevalier proved this n to infinity limit. So now it's rigorously proven. And for a similar proof on a slightly different model, but very much related, you can also look at these references. So in summary, if neurons have a memory of their spike history that is restricted to the time elapsed since last spike, that I call the age, then for mean field networks of spiking neurons, when the number of neurons tends to infinity, you get a population density equation. So now this result is very solid. It has been proven, and I think it's well accepted in the community. But the problem is that neurons, they have a memory of their recent spike history that goes beyond the last spike. And this is well known. So the recent spike history can have an impact on the spike times or the spike generation, and this is adaptation. And on top of this, if you see spikes as signals emitted from one neuron to another, the recent spike history can also modulate the effective amplitude of the spikes sent from one neuron to another. And this is short-term plasticity. So our goal in this project is to generalize this n to infinity result that I presented before for neurons with adaptation and short-term plasticity. So I'll first show you a motivating example with a short-term plasticity, and then I'll show you our general and rigorous result. So I'll take the same model I introduced, the exact same model I introduced in the introduction, and I'm going to add Sodix-Markram short-term plasticity. So a very well-known model of short-term plasticity. So now each neuron, like before, has an age variable A, but on top of this, it has two short-term plasticity variable, so a facilitation variable V and a depression variable Y. And so these variables are going to follow a system of stochastic differential equation. I write dz, the spike train of the neuron, and it's going to have intensity f of A and X. The age A follows the same dynamics that I explained in the introduction. And V and Y follow the Sodix-Markram model. So between spikes, V and Y relaxes towards a certain value. And at each spike time, V and Y jump according to a certain rule. Importantly, V and Y, variable V and Y are going to modulate the mean field input X. So one way to get an approximation for the population density equation is to take the formula I showed you before. So the formula without short-term plasticity, and introduce a correction term here that I call R. And then using some heuristic, we can derive an evolution equation for this correction term R. And this is what we did in a recent paper with Gerstner and Schwager. And this equation, this population density equation, gives a very good numerical approximation of the real density equation. However, it is not exact. So even if numerically it's quite close, we know that it is not exact. And this kind of approximation results are quite common in theoretical neuroscience. And they are a bit frustrating from the mathematical point of view, because on the one hand, you can't prove that it is the n to infinity limit, because it's simply not the case. And on the other hand, it's very challenging to get a rigorous estimate of the error we're making. So bottom line, it's hard to prove anything with regards of this kind of approximation results. So then what is the exact population density equation? And we are going to answer this question and also prove this. So based on the model with short-term plasticity that I've shown you, I'm going to introduce now an abstract model, an abstract multidimensional model. So in the introduction, the neuron had only one variable, that was the age. And so a neuron was a particle moving in this one-dimensional space. And now I'm going to add an arbitrary number d of additional variables, m1, m2, blah, 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 until md. And now you have to see neurons as particles moving in this 1 plus d dimensional space. So we call this abstract model the age and leaky memory dependent Hawkes processes. So now each neuron has an age variable, like always, and it has leaky memory variables m. So m is a d-dimensional vector, and a and m are going to follow a system of stochastic differential equation. So dz, again, is the spectrum of the neuron, and it will have intensity f of a and m. And here the dependence on m is here to model adaptation. A follows the same dynamics as always, and m has a certain drift towards zero between spike. So between spike, it drifts towards zero at speed lambda. So lambda is a diagonal matrix with strictly positive terms. And when the neuron spikes, m will jump according to a certain jump rule gamma. Now, if we look at the mean field input, the interaction function h also depends on a and m, and this is for modeling short-term plasticity. So the motivation behind this abstract age and leaky memory dependent Hawkes process is that we want an abstract model on which we can map many interesting concrete models of spiking neurons. So for example, neurons with Zoldyck-Markram short-term plasticity, neurons with a moving threshold adaptation, the multi-timescale adaptive threshold models, and also the very general kernel-based models like the spike response model or the generalized linear model, if the refractory kernel is a finite sum of exponential kernels. So we want to prove that when n tends to infinity, if I write small gamma, the jump mapping, gamma m equal m plus capital gamma m, and b, the velocity field, then the population density equation for this age and leaky memory dependent Hawkes process is going to be this partial differential equation. So you see on the first line a continuity equation. On the second line is a border condition on the hyperplane A equals 0. On the third line is the equation for the mean field input. And on the fourth line is simply the initial condition. So I won't have time to explain this equation in more detail, but you can really understand it as a multidimensional generalization of the time-elapsed neural network model of Pagdaban, Pertam, and Salor. So the first step of the proof is to show propagation of chaos. And here we will use some well-established technique for Hawkes processes that were introduced by Delattre, Fournier, and Hoffman. And so we get a theorem saying that the empirical measure of our network is going to converge to the law of the limit process, ATMT. And you can understand the limit process ATMT as the process for one neuron in the n=infinity network. It's a bit of a heuristic way to understand it. And the important thing to get from this result is that if ALM is really the correct population density equation, then the law of this limit process should give a solution to this equation, should be a solution to this equation. So this leads to the second step. So we want to go from the law of the limit process to ALM, to the population density equation. So more specifically, writing rho t, the time marginals of the law of the limit process, we want to show that rho t solves ALM, the population density equation. We're going to proceed in two sub-steps. So first, we use the limit process ATMT to construct a path integral representation of rho t. And this nicely combines ideas presented in two papers from two slightly different disciplines, so No and Gerstner and Fournier-Lejerbach. And finally, with this representation, we'll be able to show that rho t is a solution to ALM. So just to give you an intuition of what I mean by path integral representation. So let's say that I'm interested to know what is the probability at time t to be in a certain state A hat, M hat. So this is really just a cartoon. So I'm interested in this probability. And so I'm going to write this probability as the integral over all the possible trajectories a neuron can take from 0 to t, such that it arrives at time t in state A hat, M hat, weighted by the probability of these trajectories. So this is really the intuition behind the path integral representation. And in our case, we can make all this fully rigorous. So now, armed with this representation, we can prove the final theorem, which says that if rho t denotes the time marginals of the law of the limit process, then rho t solves ALM. And first, we use the path integral representation to show that rho t has the right regularity. And so this is a little bit technical, but it is actually the point in the whole proof that has required the most work. And it's also maybe where we believe our proof might be a bit original. And then once we know that it has the right regularity, it's quite easy to show that rho t solves ALM. And this concludes our proof. So in conclusion, we have proved that for a large class of mean field networks of multidimensional spiking neurons, we get, when n tends to infinity, a multidimensional population density equation that we've called ALM. So in a sense, with this work, we have given a rigorous footing for this type of multidimensional population density equation. The details of the proof can be found in a preprint on arXiv. And naturally, the next step would be to analyze mathematically and numerically this equation to better understand the dynamics of large networks of spiking neurons. For this work, I have to warmly thank my supervisors. So Eva Löscherbach supervised all the mathematical part of this work. Thilo Schweidger and Wolfram Gerstner supervised the short-term plasticity project that I mentioned. And Wolfram Gerstner is also my PhD supervisor. At the beginning of this project, I had the chance to have many useful discussions with Monia Capana and Pablo Ferrari at the University of Buenos Aires. And more recently, I've been discussing some PDE aspects with Claudia Fonte and Stefan Michler. And also many thanks to the SAM team, the math department of UBA, and my lab, the LCN. And here are just the main mathematical references related to this work in case you are interested. Thank you very much for your attention.
Thank you very much, Valentin, for your beautiful talk. So now we have time for questions. I see that there are 2 questions, and so you might ask questions in the Q&A button. So there is a first question by Dimitri Todorov. The final equation looks quite complex in the general case. In which context do you hope to analytically study it, Valentin?
So that's a very good, that's a good question. I mean, so for a physicist, the final equation is a kind of master equation, and in a way, it's not. I think on certain aspects, it shouldn't be more difficult than the classical time-elapsed neural network model, so the refractory density equation. But there are some tricks that you can use with the refractory density equation, so the time-elapsed neural network model, that absolutely cannot be used with this generalization. So for me, I'm still not quite sure in what sense this equation is easy to analyze, but I think that we can do analytic work. It's certainly more difficult than the simpler case, but I'm not hopeless that we can do analytic work. But I don't know more about that because I haven't ventured in this direction yet.
Do you see the second question, Valentin? I will read it for everybody. It's by Daniel Scott.
Yes.
Could you please say, and I also wanted to ask this question, what the regularity condition that you were evoking is actually about, this regularity on?
Yes, okay. So maybe I will try to go back to the slide. Let me see, how can I do that? Perfect. So, no, sorry. Am I sharing my screen now, right? So I said, has the right regularity. Oh, yes, well, so at the end of the first part of the proof, we have this object. So the law of a limit process. And so I wanted to be in a L1 setup, so meaning that the initial condition has a density, and I wanted that at each time, the time marginal has a density. And so the first thing that I had to show was that at each time, indeed, you have a nice density and you don't have atoms in rho. So rho is really a density with respect to the Lebesgue measure. And you could get this result with the path integral representation. And on top of that, with the path integral representation, you could get that rho t is in CL1. Unfortunately, I don't have a slide for this, but I hope this is clear enough.
Thank you. Thank you, Valentin. So if there are other participants who want to ask questions, Thilo told me that you can also wave hands. I don't know if you're able to, and it's complicated, more complicated Zoom than video conferences.
So there should be some possibility to raise a hand if you want to ask a question live. So we could do this.
Speak. Yeah.
Otherwise, maybe I ask in the meantime another question to Valentin. So you showed a result that is valid for n to infinity.
Yes.
Is there some hope that you can get some results about fluctuations for finite n?
Yes, so I don't know, I'm not at all an expert on this, but I'll see two strategies. So one is to use a bit the strategy that was used in a recent paper by Julien Chevalier, which is to, instead of showing that, oh yes, it converges to the law of the limit process, to instead of get this kind of result, to get central limit theorem kind of result. So where you have a little bit of fluctuation and you see that, when n is large, you have the right fluctuation in a sense. And so that would be one route. And so to see if we could generalize this result of Julien Chevalier. And the other way would be to have a more heuristic approach and to try if one could use the approach you used in the 2017 paper on this kind of multidimensional equation. So then that would be not something very provable, but we could test that if your approach can be applied in multidimensional population, for a multidimensional population density equation. And I don't know if it is possible, but I'm really interested to think about it.
Thank you. This is the perfect transition to the next talk, actually. So, because you have already quoted, Valentin, the paper by Julien, who is also in the audience. At least I think I saw him somewhere. So this is a good transition to the next talk. So thank you again, Valentin, for your beautiful first